This is Related Rates Part 2. Make sure that you have already watched Related Rates Part 1, where we talked about the concept of a related rates problem and did a few of the classic examples that you always see in every related rates chapter. And these three examples are also going to be pretty common examples, but they all have their own unique spin and are different styles of problems you need to be familiar with. So let's start with this one. We have Benny making a snowball. It's spherical in shape. He lays it out in the sun so it begins to melt. We are given that it melts and its radius decreases at zero point 0.2 inches per minute. How fast was the volume changing when the radius was 2.5 inches? So the key to starting this problem is the formula for the volume of a sphere. And it's 4/3 pi r cubed, and that's probably not one that most people have memorized, but it's one that you should get familiar with when you're talking about related rates. So once a lot of these problems start with a geometric formula. In this case, that's the sphere volume formula. So let's start with the info that's always true. And all we know right now, let's see, the volume's changing, the radius is changing, so this formula is all that's always true. Both V and R are adjusting, they're variables, so this formula is all we've got. So we can move straight to the derivative process. So the derivative of V is dV dt. This is the rate of change of the volume, and that's the question. How fast was the volume changing? That's dV dt. So this is our unknown. 4/3 pi, that's all constant. So when I drop my 3 down front, it's going to cancel the 3 that's already under the 4, and I'm going to get 4 pi r squared dr dt. Okay, so that 3 dropped down and multiplied by the 4/3 that was already there, canceling the 3 in the denominator. Remember, pi is a constant. Even though it's a Greek letter, it's still a constant. The 3 decreases to a 2, and we add on dr dt because we're taking the derivative with respect to time. So this one's still pretty straightforward. I know two numbers, so I need to find the third. dV dt is my unknown. 4 pi. And this is what I've called the snapshot. This is the moment in question, and that's when the radius was 2.5 inches. So I need r squared, which is going to be 2.5 squared. And we were told that this snowball is melting such a way that the radius decreased at a rate of 0.2 inches per minute. Now here's something that would be easy to forget. Negative 0.2 is dr dt. Okay, anytime something's decreasing, its quantity needs to be negative. Now at this point, we're just putting it in the calculator, either coming up with an expression in terms of pi, or just putting the pi in the calculator. We'll do both. 2.5 squared times negative 0.2 times 4 is negative 5 times pi, or negative 15.7. And we need some units here. We were asked for the rate of change of the volume, and my distances are in inches, so my volume will be in cubic inches, and my times are in minutes, so inches cubed per minute. It's the rate of change of the volume. All right, so another pretty straightforward example, but with a formula we have not used yet. Okay, next example. This one is in every related rates section of every calc book you'll find also. It's a conical paper cup. So imagine a water tank like in an office building. You've got little white cone-shaped cups that you fill up to get your drink of water and throw them away. So this is about water being poured into one of those. So what we know, water is poured in at a rate of 0.5 cubic centimeters per second. So let's talk about how fast the volume of water is changing. So we know dV dt. If the radius of the cup is 4 and the height of the cup is 10, find the rate of change of the height of the water at the instant or during the snapshot when the height is 6. So let's get this equation set up. So the volume of a cone is the formula we need to use. And the volume of a cone, it's a third of the volume of a cylinder. A cylinder is pi r squared h. And let me move that over a little bit. A cone is a third of pi r squared h. Okay, so this is a geometric formula for volume like we had on the last example. The problem with this one is that it has both radius and height in it. And this is how we're going to fix that problem. This cone of water, imagine the cup is invisible and you just see a little cone of water in there. At all points, this cone of water is a similar figure to the overall cone, the cup itself. So if the radius of the overall cup is 4 to 10, and 10 is the height, then if this thing is half full in terms of height, that would be 5 to 2. Those ratios, these are basically similar triangles. No matter what, as this cone of water expands and fills up this conical paper cup, the radius and the height are always in this ratio of 2 to 5. Now, the question asks me about height. When the height is 6 centimeters, the rate of change of the height. So I could substitute either the r out of this equation or the h out of this equation, but since the given info and the question are both about the height, I need the height to stay part of my equation. So the r is what I need to get rid of. So I need to eliminate r from my equation using this little trick. The radius of this cone of water is always 2/5 of the height. Because of similar triangles, the sides are proportional, and 4 to 10 or 2 to 5, that's always a 2 to 5 ratio. So the radius is 2/5 the length of the height. Now I'm going to use that substitution to eliminate r from my equation. Let me change 1/3 pi to pi over 3 just for the sake of space. And I want to take my r out and put in 2/5 h. R is squared, so I need to square all of that. And then I have the other h. Okay, so this is a trick that you might not have thought to do when you've never seen this example before, but it's a very common example. So it's just kind of the trick you remember to do when you see the cone problems. And now that we have r removed from our equation, we pretty much treat it like always. Before I differentiate, let me clean up some of these constants and combine them. I've got 4 pi because I'm squaring that 2, and I've also got a pi. And then I'm squaring the 5 to get 25, and I'm multiplying it by 3 to get 75. And then I'm squaring the h and combining it with the other h to get h cubed. So this is always true. Now I want to differentiate and go to the moment when the height of the water is 6. The derivative of v is dv dt. 4 pi over 75 is all constant. I'm just going to separate it and then multiply it by 3h squared. I can go ahead and multiply the 3 by the 4 up there to get 12 pi, but just for this step I want to leave it separate so we can kind of keep these steps in order. So I've got 12 pi over 75 h squared dh dt. And now I want to plug in my givens. Water is poured into the cup at 0.5 cubic centimeters per second. That's the rate of change of the volume, 0.5. And I'm going to change that 0.5 to a 1/2 because I'm kind of in fraction mode right now. 12 pi over 75 h squared. The question is, find the rate of change of the height, dh dt, when the height is 6. So I'm going to plug in 6 for h, square it, times my unknown dh dt. Okay, so at this point it's just taking this 1/2 and dividing it by some things and multiplying it by some things. Try to get this dH/dt on your own while I'm working it out on my calculator. And I'm going to go straight to the decimal answer. I've got 0.5 on the left. I need to multiply that by 75 because that 75 is on the bottom. I need to divide it by 36 because 36 is being multiplied. I need to divide it by 12. And I need to divide it by pi. And I get 0.0276. So let's call that 0.028. dH/dt. So at this instant, the height is changing at 0.028 centimeters per second. I should squeeze that in. Centimeters per second. All right, so there's another common example that you just need to memorize how to do it, how to get through this hurdle of having two variables, and that's by using similar triangles. And different problems might have different similar tricks where you use a relationship between the variables to eliminate one of them and be able to take your derivative with just one variable. Okay, last example. When you see a right triangle setup, usually you're using the Pythagorean Theorem, a squared plus b squared is c squared. In this case, the question is about this angle of elevation. We've got a person here watching a rocket launch. We've got the rocket climbing in the air over here. And the question is, how fast is the angle of elevation changing? Now, right triangles have lots of relationships. You learn early on in Algebra 1 and Geometry about the Pythagorean Theorem, and then a little bit later on you learn about trigonometry, where we bring the angles in and not just the sides. The relationship that's always true, if we're talking about the opposite side and the adjacent side of this triangle, according to this person's view, the thing that's always true is that the tangent of this angle theta equals y over 500. Now, I don't want to call that 500 like x or something like that, because if there's a quantity that doesn't change, I want to put the number in. I don't want to put a variable in unless it's actually varying. And the two things that are varying are the height of the rocket and the angle at which this person has to look up to see the rocket. So tan theta equals y over 500, always true. Now let's take the derivative and sub in the things we know. The derivative of tangent is secant squared d theta dt. Okay, theta is a variable that we usually use for angles. It's not like pi, it's not a quantity that doesn't change, so we need a d theta dt. The derivative of y over 500, this is just 1/500th times y. So the derivative of anything times y is just that constant 1/500th dy dt. Okay. And now we want to sub in the things that we know about this rocket at the instant in question. What I know is that the rocket is moving at 200 meters per second. So that's dy dt. That's how fast y is changing. So I can go ahead and make the right-hand side of this equation 200 over 500. Now the left-hand side, secant squared theta d theta dt. How fast the angle of elevation is changing is the unknown d theta dt. So I need to know what either theta is, so I can take the secant of theta and square it, or I could just figure out what secant of theta is and square that. The d theta dt I'll go ahead and put in place because that's what I need to know. And let me, I suggest this is going to be the easier way. The moment in question is when the rocket has a height of 800. So let's fill out 800 over here. Now, I could inverse tangent 800 over 500, figure out what theta was, take the secant of that and square it, or I could just use the triangle itself and keep my numbers exact. If I have sides of 500 and 800, if I square both of those and add them together, I get 890,000. Square root of that is 943.398. Just use the Pythagorean theorem on 500, 800, because at this instant the person is 943.398 away from the rocket. I'm going to have to round off anyway, so you're okay just figuring out theta and taking its secant, but this is just another option. Now, what is secant squared of theta? Secant is the inverse of cosine. Cosine is adjacent over hypotenuse. So 500 over this 943 number is, well, actually, let me just not do it that way. Let me do that secant, if cosine is adjacent over hypotenuse, then secant is hypotenuse over adjacent. So 943 point, I'm going to call it for the sake of space, 0.4 right here, over 500. That's the secant of theta, and that needs to get squared. Okay, so make sure you're comfortable with me taking secant of theta, and since cosine equals adjacent over hypotenuse, then secant, which is the inverse of cosine, must equal hypotenuse over adjacent, and I plugged in hypotenuse over adjacent to get secant of theta. Okay, so now all that's left to do is to solve those back. There we go. All right, don't need that. Okay, so at this point I'm just putting numbers in my calculator. On the right I have 200 over 500, which is 0.4, which is the same as just 2/5. And then I need to multiply both sides by 500 squared, because that 500 is getting squared. It's part of the fraction that's getting squared. I need to divide both sides by 943.4 squared. And that should leave me with d theta dt. And it's going to be 0.112. And this, think about how fast an angle is changing. An angle is measured, in our case, in radians. And so this is in radians per second. And that's going to wrap up this third example. As with anything, and especially in a case like this, the more practice, the better. And so there's 3 more good practice problems.